Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So what we are now going to be starting is chapter 4, which is a bit of a deja vu chapter. So in chapter 4, what we're going to be doing is revisiting some topics from earlier, but now we're going to be changing our focus a little bit, broadening our horizons, generalizing a little bit. So what we're going to do now is talk about vector spaces in a more general way than we have before, and subspaces. So vector spaces and subspaces. And here is our setup. So we are going to be dealing with a more general approach to a concept that we already have done a little bit. So Rn is the space of column vectors. We are going to be now looking for other things that keep all of the same important properties of that, but which might be dressed up in some kind of different costume. So the setup is we have any set, and it doesn't have to be a set of column vectors exactly. It can be any set that has the concept of addition and a way to multiply by real number scalars. So what we can say is it is a set that is equipped with addition and scalar multiplication. And the scalars are coming from the real numbers always. The set, though, can be all kinds of different things. Now, these sets may or may not be vector spaces, and that is what we are going to define now. So such sets may or may not be vector spaces. Here's what it takes. So here is the definition, the general definition. Of a vector space. All right, so if we are given a set which we'll call V, given a set V with addition of elements of V, and we'll word that as vector addition, and multiplication, and the ability to multiply the elements of V by real numbers then V is sometimes you say a real vector space to indicate where the scalars are coming from. if the following 10 things are true, for any and let's see, for any three vectors u, v, and w, all belonging to this set, and any c and d belonging to the real numbers. Okay. So, here what we're going to have are the 10 conditions that are the most important things about Rn that we would want anything that we would dignify with the name of vector space to also satisfy. So first off, u plus v has to be an element of v. So this addition cannot take you out of the set. So maybe our set is something like polynomials. If you add two polynomials, are those still polynomials? Yes, they are. Also, vector addition has to be like regular addition in that it has to be commutative. So u plus v has to be the same as v plus u. And again, thinking of polynomials, if I add together two polynomials and then I hit reset and I add them together in the opposite order, will the results be the same? Yes, they will. All right. Thirdly, addition has to be associative. So if I add u plus v first, and then building on it, I decide to add in another vector, w, that had better be the same overall result as if I did u added to the result of v plus w. So I have my option when I have these three vectors that I'm adding together. I have my option whether I want to add these two first and add this to the result, or I want to add these two first and add this to the result. It's up to me. Also, and is this true for polynomials? Yes, it is. If I add together three polynomials, it doesn't matter which two I put together first. It's all going to come out the same. So there is an element which we'll call 0. Zero in V, such that such that 0 plus u is the same thing as u plus 0, which is the same thing as just u. So it does not count as a vector space unless there is a 0. There has to always be a 0 somewhere in there. And what makes 0 0 is that it is the element where if you add it, it doesn't affect anything. So it is the additive identity. All right, 5. So for each u, there has to also be such a thing as negative u. There's negative u, which belongs to v, and what makes negative, what makes the negative do what it does is that it cancels out the original u. So u plus this negative u has to equal 0, And for that matter, that has to be the same thing as negative u plus u. Oops. So those both have to equal 0. And that's what makes a negative a negative. It is what's called an additive inverse. Alright, so this basically is the end of the pure addition properties, and now it also has to be the case that if I do a scalar multiple of u, that stays in our set V. So this is very similar to the property of subspaces, as is 1 and as is 4. And also, this scalar multiplication has to behave properly. It has to distribute, for one thing, over addition. So if I do C times U plus V, that has to be the same thing as CU plus CV. And the distribution also has to work the other way, which means we have to be able to add together our scalars. So C plus D times U has to equal the same thing as CU plus DU. So the scalar multiplication, we can distribute it either over the addition of vectors, or we can add the scalars and multiply by that. Also, scalar multiplication has to be associative, so that means if I did a scalar multiple du and I multiplied the result by c, that has to be the same thing as if I had just multiplied together the two scalars and applied that to u. And then also has to be the case that if you do a scalar multiplication by 1, it ought to accomplish precisely nothing. Multiplying by 1 should not ever change your vector. That's the whole point of 1 as far as multiplication goes. It is the multiplicative identity. Now so the elements of the set can be any kind of crazy variety of things. The important thing is, does it have addition of members from within its set? And does the addition satisfy the properties? Does it have scalar multiplication? Does the scalar multiplication satisfy those properties? Is there a 0? Things like that. So the set in question can come from a wide variety of settings. The question when we say in question, so the question is always, can we add? I guess I'll call this part I. Can we add elements from the set? And by that we mean obeying all these properties. And can we do a scalar multiplication? Also, obeying these properties. The important thing is, whatever it is that counts as addition or subtraction, or not subtraction, addition or multiplication in this setting just has to be consistent with these 10 properties. Okay. Examples of vector spaces. All right, we're going to give some examples of vector spaces, and once we have given these, so we'll do a quick reality check, make sure the properties make sense in this context. But once these examples are in the book, then we can just appeal to them, and you don't have to separately prove them each time. So first off, Rn. So Rn is the classic space of n-dimensional column vectors. So Rn. So this is the set of elements of the form, and we might write it like A1 down to AN, such that the A1 through AN are all real numbers. Are each real numbers, I should say. So this one is classic example of a vector space. Okay, so here's another example of a vector space that is a little bit more exotic. So complex numbers. So these are things of the form a plus bi, where again the a and the b are real numbers, and then I is of course the famous imaginary number, the square root of -1. So this is the set of complex numbers, but this particular set does indeed satisfy all these properties. You can add together two complex numbers, the result will be a complex number. You can multiply a complex number by any real number, and the result will be another complex number. The addition and the multiplication are all completely in conformity with these 10 rules, and there's nothing weird about it. I mean, it's a little weird to be talking about imaginary numbers in there, but no property would be failed. There is a 0, and that 0 is the number 0. So that's in there too. P. So this is the set of polynomials. Polynomials. So that's the set of everything of the form, and I might write it like this: a0 plus a1t, I'll use t as my dummy variable, plus a2 t squared up to some highest term. So up to a k tk, where the a's, so a1 up to ak, are all real numbers, and k is some natural number, so some counting number like 1, 2, 3. So there's one. But we can also cut it, we can restrict ourselves a little bit here and do Pn. So this is polynomials. Of degree at most n. And then that, as a set, looks like, well, now we have a fixed we have a fixed boundary on how high the degrees are allowed to get. They're allowed to get up to n. Oops. And the AI up to A1 up to AN are all real numbers, so the coefficients are all real numbers. And that also qualifies. So you can use either a colon or a bar to separate out the parts of your set builder notation that that go from the recipe and then the ingredients. So those are some examples, but there are other examples too. So other examples that don't necessarily have names like this, but you could say the set A times sine t plus B times cosine t, where A and B are real numbers. And the question would be here, if I have things like this, so like 3 sine t plus 1/2 cosine t, things like that, things of that form, can I add those things and will the results still be in the set? Yes, I can. Can I multiply them by a scalar and get something that's still in the set? Yes, I can. So things like this would still be in the set, and this is a smaller case of what are called trigonometric polynomials, which we'll look at right at the very end of the class. And other things that might also be included here would be something like, and here we won't necessarily write these because we won't really use them, but those of you who have dabbled in Math 253, you will have seen sequences and series in that class. And those also are both cases of vector spaces. So a sequence is just it's just like an ordered set of numbers. So it's just number after number after number after number. And if you wanted to add together two sequences, you just add them entry by entry. If you wanted to do a scalar multiplication, you would just do that scalar multiplication entry by entry, and it all makes perfect sense. Similarly, a series, an infinite series. So if you had something that was like a power series, for example, you could take one power series, you could add it to another power series. The result would be a third power series. You could take any power series, you could multiply it by a scalar. The result would be another power series. And now let's look at some sets that are not powers, or not vector spaces. So sets that are not vector spaces. So here we will always try to find a property that fails. So find a property that fails. Okay, so let's take as an example, how about the subset of R2? So sets that are not vector spaces, so we need to find a property that fails. So let's take a subset of R2 that consists of all the points on the unit circle. So the subset of R2 consisting of the points of the unit circle. So if I wanted to make that nice and nice and rigorous, I could just say the set of all points xy, set of all points xy such that x squared plus y squared equals 1. Okay, so looking at this, is this a vector space? Well, it is not. And in fact, it is not in basically every way. So you can take points of R2 and add them together, but if you take 2 points that are on the unit circle and add them together, will the result be on the unit circle? No. Is 0 on the unit circle? Nope. The unit circle goes out and around. These are all the points that are distance 1 from the origin, so they don't include the origin. And usually that's the easiest thing. So we'll call this W. W will be a generic name. We'll use capital W, capital V, things like that. We use W when it's more doubtful because V carries with it some baggage, assuming that it sort of is a vector space. So, for one thing, 0 is not in W. How do I know that? Because 0 is an element of R2, but 0 squared plus 0 squared is most certainly not equal to 1. So it fails the condition that is in the set. Okay, so this one is not. How about the first quadrant of R2? So that would be, if we wanted to write that out as a set, so we're talking about elements of R2, so they all have the generic formula xy, and then we just have to say what the x and y have to satisfy, and to be in the first quadrant, we'll say that even includes the coordinate axes. So this is quadrant 1. So in quadrant 1, it's everything over here. So those are places where the x and the y are both positive, or we can even say x is greater than or equal to 0, y is greater than or equal to 0. We'll include the boundary just to be on the safe side. Well, is this a vector space? Well, can you take 2 elements of the first quadrant and add them together and get another element that is in the first quadrant? Yes, you can. Can you is 0 in this set? Yes, it is. Can you do a scalar multiple of elements of this set? Answer is not always, because if you take a scalar multiple of an element in quadrant 1, and that scalar is negative, then you're falling out of it. And in particular, so the answer is so this is not a vector space. And they are all not vector spaces. Not a vector space. And one way we could do this would be to just let u equal something that is in the space, 1, 1, is negative u in, so u is in W, but negative u, or negative 1 times u, is not in W. Okay. So there's another example of the way you can fail to be a vector space, even if you can add together 2 elements, even if 0 is in there. It might fail on the scalar multiplication. Let's go with another one. Let's take one from the land of polynomials. So let's say C. Polynomials. of the form 1 plus AT plus BT squared. Where the A and the B are allowed to be any coefficients from the real numbers, but we've got that 1 there. Well, is this a vector space? It is not. And the reason, well, there's a lot of reasons, but that 1 really messes us up because that means that 0, the polynomial of 0, is not in there. So 0 is not in W. Also, if you were to do any scalar multiple other than 1, you would be messing up the format. But once you've proved your point, you can rest on your laurels. Now, showing that something is not a vector space is one thing. Showing that something is a vector space is often a little bit trickier. So one way, the easiest way often, usually even, to show that something is a vector space is not to go step by step through all 10 properties. That's too cumbersome. The easiest way to show that something is a vector space is to show that it is a span. So note, any subset of a known vector space for which we can find a spanning set. So that means, i.e., a collection of vectors whose span is W is automatically a vector space. So this is almost always the easiest way to show that something is a vector space. This is almost always the easiest way to show that a set is a vector space. So to show that a set isn't, you have to find a property that fails. Usually the lowest hanging fruit on that is look for 0. If 0 is not in there, then that's usually an easy thing to check, and it's usually the quickest way to guarantee something is not a vector space. However, to show that something is, it might require as much as showing that it satisfies 10 different properties, which is a bit of a tedious process. So if you can just find a collection of vectors that span the set, then you've got yourself a guaranteed vector space. So an example. So let's say that W is equal to, and the way these will often look is something like this. So it's going to be a collection of vectors, let's say in R3, and let's say they look like this. A minus 2B plus C, 2A minus C, and B plus C, where the A and the B and the C are allowed to be any real numbers. Well then, think about what it means to be an element of this set. So to be an element of this set, so let's say we've got a U that's in W. So let's say we got a, I don't want to use the letter U because in your book, in the textbook homework, they use the U slightly differently. So let's say you've got any X that's in the W. So X is in W. Then what that means is that X is equal to something of this form. This is exactly the specifications of the elements of this set. Which we can then, what we can do here is we can try to separate these things out by the parts that have A and the parts that don't, and the parts that have B and the parts that don't, and the parts that have C and the parts that don't. So we go A, 2A, and 0 plus minus 2B, 0, and B, and then plus C minus C and C. And then what that means is that if we pull out an A, we'll have 1, 2, 0. If we pull out a B, then we'll have minus 2, 0, 1. If we pull out a C, we'll have 1, minus 1, 1. And what this means is that X is in the span of these. 1, 2, 0, minus 2, 0, 1, and 1, minus 1, 1. So X is in the span of these. So that means that W equals the span of these three vectors. Because W is exactly the set of all the combinations of these sorts of things that you can make. And if you know that it is a span, then you know that it is a vector space. All spans are vector spaces. When you start allowing all the arbitrary linear combinations of things, then by default, you end up having something that is closed under all of the appropriate properties. And if it is a subset of a known vector space, then you know that the multiplication and the addition behave properly. Now, this is a very common category of problem that we'll have, and in categories like this, where you have a set given with a recipe like this, what you want to look out for is that there are no terms of this that are completely missing any of these letters. So if there are any constant terms in there, then that is going to end up messing up the ability to write it as a span. Because if this had been b plus c plus 1, then we would have some difficulty with scalar multiplication, or the 0 wouldn't be there, or the addition wouldn't be closed. All kinds of things would go wrong. So here's the tip. So if you have something of a form like this, and you see a naked constant that's not 0, then that should raise a red flag that it's probably not a subspace or a space. So if the format of the set includes a non-zero constant term, by which I mean missing a parameter, then that should be a red flag that this is most likely not a set, or not a space. Then it's probably not a vector space. And in that case, look for scalar multiplication or the absence of a 0. If there are no such constant terms, you will usually be able to pull it apart into a collection of spanning vectors. So here's an example of that in action. So let's say that we have W equals, and then let's say what we have is just A minus 1. Then here we have 2B plus C, and then down here we have just make it actually 2B plus A, and then here we have A plus B. So it's the set of all of these, and then we'll say A, B, and C are allowed to be any real number. Okay. Well, if this is truly a vector space, then it should include a 0. So is 0 in W? So that's the question. So if it is, so we're talking about 0, 0, 0 has to equal A minus 1, 2B plus A, and A plus B for some choice of A's, and B's. So looking at this, so if A minus 1 equals 0, that implies that A equals 1. Okay, so far no contradiction. But then if 2B plus A equals 0, and I know that A is forced to be 1, that means 2B plus 1 equals 0, which means that B is equal to negative 1/2. But then, is it possible for A plus B to equal 0? Well, that would mean that A equals negative B, but that's not the case. No. So 0 doesn't match the format. It doesn't fit. Doesn't fit the format. So it's not in W. W is not a vector space. All right. Now, let's take a look at an example of a polynomial case. So here's an example. What if we are talking about the set of polynomials of the following form? So the set of polynomials of the form at squared plus c. And now we're missing, there's no term of just t. Is that okay? So A and C are in R, and we have to try to figure out what we can figure out. So here we're not talking now about the classic case of Rn. We're talking about polynomials. But I can still just take a generic element and see if I can rewrite it as a span. And the reason why I'm going that direction is I don't see any parameterless terms here. If this had been at squared plus 2, I'd be immediately suspicious. But here I do not see anything like that, and so I'm of the belief that this probably is a vector space, and I want to write it as a span. So then, what we have here is a t squared, so a generic element of W, at squared plus c. Well, then what that means is, so it's not written in the normal format that we'd write vectors in, but technically I've got two polynomials here, t squared, and just the polynomial that's 1, and it turns out then that x is in the span of them. So that means that W equals the span of those. And so W is a vector space. All right, now let's take it into a slightly crazier direction. Also polynomial though. So let's take as an example the set of polynomials of degree at most 2 and we'll say P of t such that P of 0 equals 0. So polynomials are functions. You can plug numbers into functions. So what about this? So what if I take the set of all the polynomials of degree at most 2 such that P of 0 equals 0? Well, what does that mean? So we're talking about P of t is equal to a t squared plus bt plus c, and I know that P of 0 is supposed to equal 0. But I know how to evaluate a polynomial. It's a of 0 squared plus b of 0 plus c. And if that equals 0, that means 0 equals c. So what that means is that P of t is equal to a t squared plus just bt, which means we have a span. We have a spanning set here. Which means P of t belongs to the span of the polynomial t squared and the polynomial t. So this looks different. It looks very different from vectors, but it's actually not so different. It's just a matter of trying to rewrite it so that you have clearly combinations of some basis here, t and t squared. So that means the set is a vector space. All right, and then the last version of this that we can see that we're going to look at is a case where the set is defined in a way that involves certain equations. So we might have a set A, B, and C for the entries of a vector, and then over here we're told some relationships between the A, B, and the C. We're told maybe that A plus B equals 0, A plus C equals 1, and we're told maybe that B equals, let's say, C plus B equals 0. So let's say that these are the three relations that define the elements of this set. Oops. All right, well, I'm suspicious because I see a number. When you see a number that's not attached to a letter, this makes me suspicious. So I'm very suspect. So I suspect it's not a space because of that non-zero constant. So let's ask ourselves, is 0 in W? Always go for that first. That's usually the easiest thing. So 0, 0, 0. So that means that A equals 0, B equals 0, and C equals 0. But we have relations between the A, B, and C. But A plus C equals 1 would be false. So that means 0 is not of the correct format. And W is not a vector space. Okay. So, there we go. That's how we answer questions like that. So in this section, we are looking at things that are defined a little differently from how they were defined before. And our task is to try to suss out whether the things that are being defined in this way are or are not vector spaces. And what it means to be a vector space is a whole host of things. But what it's equivalent to is being a span of a small collection from a known vector space. So if you can show that that's the case, then you're in pretty good shape. And you know for sure that it is a vector space, and the way you do that is you pull apart the terms so that you can get them in terms of a parameter times an element of the vector space. Now, if on the other hand there are constant terms floating around in there, then what that probably means is that it is going to fail. And if it's going to fail, the easiest property to check is the 0. So the 0 being of the format designated by the set. That's the most important thing to try to determine. And if it's not, then it's not a vector space. Alright, well that's going to do it for us now, and so I'll see you for the next episode of Math 261, which will pick up from here in section 4.2. So till then, bye.